We have a very strong partnership with AIIMS, All India Institute of Medical Sciences, which you are all aware about. Significant research investments, partnerships with the leading hospitals in the country like AIIMS. And then be it quantum technologies or other area of research, smart manufacturing, materials, energy, chemicals. We practically have strong and leading research programs at IIT. As a prospective students, you may be also interested to know that we publish about 4,000 research articles every year, and this is one of the leading number in the country. We have strong internationalization, international programs, and I'm sure maybe as a part of your stay here in IIT, you will be able to participate in these international programs. Those who are interested in masters, we have joint masters program, for example, with the University of Sorbonne in Paris. Those who are interested in joint doctoral research programs, we have a very large research partnership or academic partnership with the University of Queensland in Australia, where there are about 130 PhD students who are pursuing their joint PhDs with IIT Delhi and University of Queensland. For semiconductor research, we have a strong program with NYCU in Taiwan. We have about 150 students who are doing either their master's or PhD on our campus, international students on our campus, and a significant number of students who are coming to IIT Delhi as a part of their semester exchange or for research, and a significant number of IIT Delhi students going abroad to different universities worldwide for internships, for semester exchange programs, and so on. So I think internationalization is important to us, and I think those who are interested in masters or PhD would be highly benefited because of your stay here. Maybe that's what I would like to say about the institute. My colleagues will talk more about it. Coming to postgraduate education, of course, there are lots of opportunities these days to pursue a job or entrepreneurial activity after your bachelor's degree. I would also like to mention that we have also a strong innovation system, startup ecosystem here. At the moment, I don't know whether you get to see the research and innovation park today or not, but we have some 200 startups currently incubated at IIT Delhi. And IIT Delhi is one of the leading incubator or accelerator in the country. Several of our alumni have contributed a lot to the entrepreneurship. Out of some 75 unicorns that have come from the country, from India, about 30% of them are founded by IIT Delhi alums. You might have heard about the names like Flipkart, Meesho, Tata 1MG, and actually many more. Those were founded by our alumni. Coming back to the education, I know as India is growing, our economy is expanding, there are enormous to pursue a job or an entrepreneurial activity of after your bachelor's degree. But I still feel that if you ask me my personal opinion, I would still go a master's degree or a PhD degree just to expand your horizons. It's not about earning a second degree, but it's also about getting exposed to what is happening in research, what is happening in technology development, what is happening in the startup ecosystem. And IIT Delhi will give you a first-hand experience of what is happening in terms of cutting-edge research or startup ecosystem. And in this view, I think the postgraduate education, which is going to give you a broad base for rest of your career, for 30, 40 years in your career. And therefore, to me, the postgraduate education is very important. Of course, you may be interested in pursuing a startup or entrepreneurial activity, but you can always do that after your master's or PhD, and maybe in a much better and informed way. So with that, I think I'm almost end of my 10 minutes of time that is given to me. So On behalf of IIT Delhi, once again, I welcome you and encourage you to consider IIT Delhi as an option for your postgraduate studies. So thank you very much.
Thank you, Professor Buba, for sharing this big landscape of the Institute. Now, may I please request our Dean Academics, Professor Dhanya CT, to kindly share her words and her message for the event.
Good afternoon, everyone. Welcome to IIT Delhi and to this particular event, Anveshan, where we are giving you a glimpse of our vibrant campus, an opportunity to interact with our faculty members, and the kind of the state-of-the-art research we have been doing in IIT Delhi and our some unique features. We had a PPT to show you, but I could understand that Vivek has already stolen that script. Almost all the information is already given to you. But nevertheless, I am going to take you through this because we have some pictures, and when you see in pictorial form, you will remember it in a better way. So I don't understand how you have exactly stolen my script. That's something which is surprising. Anyway, so to let you, IIT Delhi, most of you know already who we are. So we are established in 1961 as College of Engineering and Technology in Delhi. And in 1963, we are declared as the Institution of National Importance. And in 2018, again, the Institution of Eminence tag was given to us. In the ranking, whether it is in the QS ranking or NIRF ranking, we are in the top, sometimes between first rank and second rank. And some of the departments are also always keeping the first rank. For example, electrical engineering department, computer science, and all those things. So even though we do not want to boast ourselves, this is something we have been, the ranking we are keeping in the world ranking and the engineering and technology. Right now, we are in the top 50, and the rank has been increasing over the years. Now, as Vivek mentioned, we have 3 campuses. You are in the main campus in Hoskas now, and we have a campus we started 3 years back in Abu Dhabi, where we are running 2 PG programs and 3 UG programs. And also, we have a kind of satellite campus 50 kilometers from here in Sonipat, where we are going to start some of the niche research area focused activities there. So if you have a chance to visit the other campuses, yes, you are welcome to do that. So this is the campus where you are right now sitting. It is sort of a self-sustained campus where you will find all the facilities you need inside the campus. And here you can see the boys' hostels here, and the girls' hostels in this side. We have like north and south there. And then right now you are sitting in the lecture hall complex here, which is situated here, where all the teaching activities are taking place. So if you wish to have a good look at the campus, there is a 360-degree virtual campus tour available in this. If you are visiting this website, international.iitd.ac.in campus tour, and then maneuver there, you will be able to see the whole things inside, all the facilities inside the campus. Now, IITD numbers, we have students of around 13,000 students in the campus in the form of full-time and part-time. It's an ever-growing community, and faculty of around 650 approximately. The numbers you have seen in the video might be a little bit different from the numbers I am showing here because it's ever-changing. And as mentioned before, we are significantly now a PG community with 40% of the students from the UG community, BTech and other UG programs, and 60% of the students, 4,000 masters and 3,500 PhD. As Vivek mentioned, we are graduating close to 500 PhDs per year in the recent convocations. And our ever-growing alums like 63,000, sometimes 65,000, so it's spread all across the world. And in this campus, we have 16 departments. I'll show you which all those departments are. 11 centers, academic centers, 6 schools, and 21 COEs. And these are the details of the departments. All the major disciplines you will see: applied mechanics, civil, chemical, electrical, and mechanical. All of these are the engineering discipline. We have 3 major departments in the physical sciences and also the humanities and management. Coming to the centers, these are the 9 centers where we take research to another level. These centers are formed to strengthen the research in that particular area. We have the CARE applied research in electronics, biomedical engineering, rural development and technology. So you explore the website, you will get a more idea about what these departments are doing and what kind of research outcome they are producing. Apart from that, we have schools also, essentially, to focus on the kind of emerging areas in that particular field. For example, School of Information Technology, School of Artificial Intelligence, and School of Public Policy, etc., have recently come up. Now, we have almost all the facilities needed for the PG research and for the research outcomes. We have a very strong central research facility. And also we have a nanoscale research facility. These are some of the facilities I'm showing just to show an example. But once you explore the campus, you will see more and more facilities even housed inside all these department centers and schools itself. Now, since you people are PG focused, masters and research, just for information, we keep on evolving these areas, but at present, Institute is focusing or taking its research ahead in 6 or 8 thematic areas, which you can see here. Of course, AI/ML tops the list, healthcare and medtech, manufacturing and industry, smart and sustainable infrastructure, advanced materials, energy sustainability and climate change, quantum technologies, and next-gen communications. So these are the areas which we pay a lot of attention or pool in all the research in the form of baskets. And IIT Delhi, as mentioned before, we have a unique innovation or startup culture, and we focus a lot on translational research. So these are some of the noteworthy technologies translated by IIT Delhi in the last 3 years or so. You can have a look at that, please. And we have dedicated technology and business incubation units. This is not only reserved for UGs. We could see that in the past years, most of the PG students are also very much interested in these kind of innovation and incubation units. So in this campus, we have the TBI program, and also in the Sonipat campus, we have the Technopark there. Please explore further details of this. All these information is available in the website too. Now, since you may wish to have some information about the kind of PG programs we are floating across all the departments, schools, and centers I have shown, this is almost all the academic units float their own PhD programs. So we have essentially 31 PhD programs, 41 MTech spread across all the departments, and MSR, Master in Science in Research, Master of Business Administration, Master of Science, MSc programs. We have 6 MSc programs, and a specific Master of Public Policy program, an MA in Culture Science and Science Thoughts, and Master of Design, and then 2 PG diploma programs. So all of these programs have websites of their own. So please go through the course list and the kind of flavor these programs are offering. Now, in addition to these programs, which we are floating by ourselves, we are also going global. So there are some global research partnerships, PhD and masters, to highlight. We have a joint PhD program, 2 joint PhD programs, which we started in 2018. One is with the University of Queensland, Australia, and another one is with NYCU, Taiwan, specifically focusing on semiconductor technologies. Apart from this, last year, we have started another joint program, both PhD and masters, with the Sorbonne University. We are, of course, exploring and going to start more such kind of the programs in the near future. And then kind of internationalization. This internationalization not only limits with the joint programs, it also involves kind of MOUs and co-guidance of students also. So you can see the kind of MOUs we have entered with many other universities across the world. Now, I just want to highlight these 2 slides. So in the last year, we have undertaken a very intensive curriculum review of course, of all the programs, BTech, Masters, and PhD, I would like to highlight the changes we have undertaken or implemented in the Masters and PhD. In the Masters, we realize that Master's students need to be industry ready, and there need to be more exposure for them in the curriculum itself with industry partners. So kind of mandatory internship is now integrated into the master's curriculum, and there is a lot of flexibility for the students to derive their own curriculum. So open credits or open courses are there. You can decide, even though if you are doing, for example, a master's in, say, chemical, you can decide some courses to be taken in AI, ML, or any other area which you are interested. So you can essentially derive and design your own curriculum for these 2 years. And then, according to the recruiters, they need someone who know teamwork and all. So we have integrated something called Cornerstone Project during the winters, in which students will work together as a group on a very interesting problem chosen by them, and they will come out with some research outcomes. And then there are flexible pathways. Even though you have joined in one degree, in the middle, if you are realizing that this is not for me, maybe I need something more. For example, if you have joined in an MTech program, and over the time, in the first semester, you are realizing that I am very much interested in PhD. So there is a flexible pathway. You can always convert to that, but of course, there are some criteria for that, minimum CGPA and all. You can have a look at the information brochure. So MTech to MSR, MTech to PhD, all these flexible pathways are there. And also in the last year, the recent curriculum review, we have also implemented exit pathways. You can just, out of some emergency, you can just check out from the program and get back in, something like that. So explore that more. And coming to the PhD, we focused a lot in the last curriculum review, and we decided that for the PhD, the outcome is that we want students to be independent researchers with critical research thinking. And these 3 components, research communication, research ethics, and research empowerment, we have integrated into the PhD curriculum. You will know if you are joining here what those are and how your communication skills are getting enriched, and that will help for the employment as well, not only to demonstrate your or communicate your research outcomes, but for other purposes also. Now, with this, these are the links which you might be interested to log in and see the further information on that. So this is the IIT Delhi main page, where the application portal is open today. And please visit that, and you will get the information brochure here, which is the updated one. And then there is a dedicated academics.iitd.ac.in. There is a tab for the prospective students. Please do visit that to know more about admission, financial assistance, and the vibrant campus life or the campus community, and the hostels and other kind of facilities available in the hostel. So this is the portal for the application, which is open today. Yeah, that's all from my side. Thank you.
Thank you, Professor Dhania. And I would request Professor Shomik Siddhanta, the other faculty coordinator, to please let us know how the day is going to proceed.
Yeah, so let's buckle up for the real action now. Okay. So thank you, Professor Dhania and Professor Bua, for the wonderful presentation. So we could know a lot about IIT Delhi. But I will also like to inform you that we are wearing these badges, and some of the students are also wearing the badges. So you are free to talk to them, ask them about the student life on campus. Okay, and feel free to move around the campus today. It's a holiday. It's relatively empty. All the streets are empty, so you can easily go around, but not before you attend all the sessions. Okay. Okay, so without taking much time, I'll just walk through you what you can expect today. So we begin our first thematic session, which is on transformative healthcare in this very hall. And we'll explore the world of biomedical and assistive technology. So this is a panel discussion moderated by Professor Arath Kalra, featuring from biochemical and biotechnology, mechanical engineering, and biological sciences. So they will discuss how we are building the technologies and will actually redefine patient care and human capability. So following this session, we'll have a second session, which is on advanced materials mechanics and quantum technologies. Sajesh Thomas from the Department of Chemistry, and will be a series of talks. So we'll hear from leading faculty in physics, material science, chemical engineering, and chemistry about how breakthroughs at the atomic level and in the material science are the way for the next generation of technologies. So finally, our most awaited session will begin for digital frontier titled AI, Data, Supercomputing, and Quantum Computing. So this will be in the form of discussion, moderator Sudipan Saha, and it will go into the digital architectures that are shaping our world. We will hear from the experts in AI, electronics and information technology, and how data and intelligence are converging to solve complex problems. But Anveshan is not about only talks and sessions. So it's about interaction and seeing innovation in action. So immediately after all these sessions, we will be moving to the LHC foyer where you entered at the front. So which is really the highlight of the day, I'll say. So we have for displays and demos, the outcomes of research Center of Rural Development and the Department of Design. And this is your chance really to walk around and interact with and also the different stalls and all the fun activities which will go on there. We also have a lot of fun games by the Research Synergy Forum, or RSF, which will start at around 4:35. So it's a chance to actually break and connect with the student community here at IIT Delhi. And another most important aspect of this event are the poster sessions, which will be manned by the students of different faculty. You can go around and see where you fit in. Suppose you're interested in many of these researches go on parallelly in different departments. So you can actually choose or see which department suits you the best according to your interest. Okay, and finally, I would like to acknowledge the people without whom this event would not have been successful, particularly the Associate Dean of Outreach and New Initiative, Professor Shilpi Sharma, my co-coordinator, Professor Sumitaba Mukherjee, our outreach staff, particularly Mr. Shaksham. A big thanks to the student coordinators too, Abhay, Ishant, Lakshay, and all the volunteers who will be here during the demo and the poster sessions. So we have a packed and exciting schedule ahead. So I would encourage you to participate actively and make good use of the time here in IIT Delhi. Thank you, and we are ready to begin our sessions, right? Yeah.
Okay, so let's start. I think we have got a very helpful bunch of information that you all can make use of. And we'll have 3 back-to-back sessions now. Starting with the first one, just to make the point that all the 3 sessions are thematically arranged in line with what Professor Dhania showed and Professor Vivek mentioned regarding thrust areas of the Institute. So the first thematic session is on transformative healthcare, where we focus on biomedical and assistive technologies. We have faculty members from multiple academic units. Professor Ravi Krishnan from Department of Biochemical Engineering and Biotechnology. May I please request the faculty members to kindly come on the stage as we start. Professor Ravi Krishnan from Department of Biochemical Engineering and Biotechnology. Professor Varun Ramamohan from the Department of Mechanical Engineering. Professor Arath Kalra from the Center for Biomedical Engineering. Professor Saran Kumar from the Kusuma School of Biological Sciences. Professor Arath Kalra is going to moderate the panel discussion. So let's get started for the day.
Hi everyone, nice to meet you. I'm Arath Kalra. Before we begin, I'd like to thank the previous speakers, Professor Dhanya, Professor Shilpi Sharma, Professor Buba, and Professor Soumik Siddhanta and Sumitava. Now, before we begin the healthcare session or the bio session, I think it's crucial to ask you one very important question, okay, before we begin this whole thing, and that is, आप लोगों को पता है एक लैपटॉप कितनी पावर यूज करता है? नंबर पता है वॉट्स में? किसी को भी? 10 वॉट, 20 वॉट, 50 वॉट? यहाँ कोई ना कोई तो इलेक्ट्रिकल इंजीनियर या कोई इलेक्ट्रिकल इंजीनियर बनने वाला होगा, नहीं? इलेक्ट्रॉनिक्स, फोन का पता है पावर कंजम्पशन कितना है? क्या यार, आप लोग दिन में 2 बार बैटरी फोन लगाते हो? आईफोन ठीक है, मैं बता देता हूँ, कोई बात नहीं. लैपटॉप runs on about 80 watts. Okay, a phone, an iPhone runs on watts. आपकी ब्रेन जो है, आपकी ब्रेन बस 20 वॉट्स ऑफ पावर पे चलती है. 1/4 एक लैपटॉप के और रफली डबल आपके फोन के. तो आपका जितना भी कॉन्शियस एक्सपीरियंस है, जितना भी इमोशन आता है दिमाग में, लव, हेट, stress, feeling sleepy, feeling of wanting to go out and have fun, all of this, maths, physics, computer science, English, Hindi, all of this is just 20 watts. So that is the power of biology, and that is the power of healthcare. Okay, we heard of a lot of famous IIT alumni, right? Raghuram Rajan, Divya Dwivedi, Subramaniam Swami, Chetan Bhagat, Kiran Bedi, right? The list goes on, right? इनमें से बायोलॉजी वाले इतने सारे नहीं हैं, क्योंकि बायोलॉजी डिपार्टमेंट्स जो हैं, हेल्थ केयर डिपार्टमेंट्स जो हैं, वो रिलेटिवली रिसेंटली आए हैं. इंडिया का हेल्थ केयर रेवोल्यूशन जो है वो रिलेटिवली रिसेंट है, फ्रेश है, अभी अभी हुआ है. ठीक है, और आज हम इस रेवोल्यूशन के बारे में बात करेंगे. सो वी इन IIT Delhi actually have 3 departments of healthcare technologies. One is the Kusuma School of Biological Sciences. Professor Saran, who's sitting on the rightmost side, has kindly. Please, can you put your hands together for Professor Saran once? Then there is the Department of Biochemical Engineering and Biotechnology, which is led over here by Professor Elangovan here. So please. And then there is the Center for Biomedical Engineering, which I am the representative of. And don't worry, you don't have to clap for me. But I'll tell you. Okay, thank you. I appreciate that. But I'll tell you one crazy thing about biology and about healthcare sciences is that you don't actually need to be a biologist to understand some of the important questions in healthcare technologies. So several professors and several faculty members and even several Nobel laureates in biology who are not actually biologists. Charles Darwin biologist नहीं था, Watson biologist नहीं था, Crick biologist नहीं था. ठीक है, इसी तरह से हमारे यहाँ जो प्रोफेसर वरुण हैं वो भी biologist नहीं है, वो एक mechanical engineer. And he works in operations research, integrating healthcare with India's needs. So please put your hands together one last time for Professor Varun. So these are the 3 biology, the healthcare departments, okay, in IIT Delhi. And like I said, so the Kusuma School focuses on understanding fundamental sciences, the actual biology of healthcare. DBEB, we like to call it, Department of Biochemical Engineering and Biotechnology, as the name suggests, tries to understand the technology and converting the science into technology, converting knowledge, knowing something, into a device. Okay, and Professor Elangovan will talk a little bit about that. Finally, CBME is the Center for Biomedical Engineering. Unfortunately, ये technology जो मैंने अभी कहा, हम लोग 20 वॉट चलते हैं हमारी ब्रेन, वो कभी कभी टूट जाती है, राइट? हम लोगों को डिजीज हो जाती है, कोविड हो जाता है, काफ़ी सीरियस डिजीज हो जाते हैं कभी कभी. इनके बारे में समझना, इसको ठीक करना, इसको बायोमेडिकल इंजीनियरिंग कहते हैं. ठीक है, सो दैट्स व्हाट CBME over here does. All of these programs are ripe. Gate is just around the corner, right? The eligibility. Please come to us. Please apply if you're interested in more fundamental questions or more biological ones. go for KSPS, Kusuma School. If you're more interested in the Department of Biochemical Engineering and using the knowledge to build a device, please apply to DBEB. If you're interested in more medical facing questions, apply to CBME. Okay, and these are the eligibility criteria. Keep photo lo agar chahte ho, theek hai? Now, one fascinating video that I thought I'd sort of start this panel discussion by was this one. यहाँ पे हमें क्या दिख रहा है? यहाँ पे हमें एक कॉकरोच दिख रहा है, ठीक है? लेकिन इसको गौर से देखो, ठीक है? जब जब ये आईफोन लेफ्ट स्वाइप कर रहा है, कॉकरोच लेफ्ट मूव कर रहा है, एंड जब जब आईफोन राइट स्वाइप कर रहा है, कॉकरोच राइट स्वाइप कर रहा है. इसने अपने आईफोन से कॉकरोच का दिमाग कंट्रोल कर लिया है. Are you seeing this? This is there you go. This is actually true, right? This is shocking. This is what biotechnology, biochemical engineering, biomedical engineering are capable of doing. Okay, imagine if I was able to control your brain like this. I mean, it would be a disaster, right? This is something at the nanoscale. Here we can see that you can almost see this walking kind of motion. There you go. There's this nano machine walking at the nanoscale inside a protein filament over here called a microtubule. It turns out that these machines are there in every single cell of your body. Okay? It's actually with this respect that I'm going to open today's panel discussion. Okay, so we're going to open with Professor Elangovan here. मैं भी बैठ जाता हूँ इधर. So Professor Elangovan, I understand that a lot of your work revolves around molecular machines. Can you talk to us a little bit about your work and tell us how exactly it is transformative?
Hi, good afternoon, everyone. So thanks, Sarath, for this opportunity. I think very good to see so many young researchers coming to IIT Delhi. So I'll tell you what's my background is. I'm basically a biophysicist by training. We use microscopy to see things that you don't see in your eyes. Our eyes, the smallest thing that you can see is about. What is the smallest thing you all can see with your eyes?
Say that again.
That is a visual spectrum you're saying, but what is the smallest dimension you can see? The smallest thing that you can see with your eyes. 1-2 nanometer. I think about thickness of your hair, right? It's about 100 micron. Now, why this dimension is important for us to think is, much of biology, we are seeing happening, is happening below these dimensions. So you have different types of cells. Inside the cells, you have different types of proteins which are executing things. What you saw, a video of a motor which is basically taking a cargo from one part of the cell to another part of the cell. If a cell has to divide, there are different part of proteins which will basically break the cell into two. Your heart is beating. That is kind of a protein called myosin. You are flicking your fingers. That is because you are able to execute using your skeleton muscle. Your brain is working because there are motor neurons which is transmitting the different chemicals from your tip of your toe to your brain. So whatever that is happening in a biology, they are all executed by proteins we call as molecular machines. That means these are machines that are at the molecular level. Now we would like to understand them so that we can actually cure some diseases. There are various heart hypertrophy, which is basically a mutation in these motors. That if you are able to understand what kind of a mutation is causing the disease, you can come up with a therapy. Now, we are also interested to understand these motors because we would like to create better machines. You know, what is the best machine that we have created? When we are an engineering institute, we are supposed to create different types of machines, right? What does the machine do? It can convert a chemical energy into a mechanical work, right? So all your petroleum and other different engines, 4-stroke, 3-stroke, right? So they are essentially converting the chemical energy into a mechanical energy. Now, one of the motors that I am going to tell you is present in bacteria. So this bacterial motor is able to rotate close to 2000 RPS, rotations per second. I'm sure that now you're all growing up, you will be driving a car or some motorcycle. So you will have an indicator which shows how much RPM your engine is able to rotate, right? That is in RPM. So maximum you go when you press your accelerator is 2000 or 4000 RPM. That's in your Ferraris. Now you have biological motors, which is only 50 nanometer in size, that can go 2000 RPS. And this is a marvels that we have in biology. Now, if we are able to understand these machines, we are trying to get better machine designs. We are trying to understand this to solve some of the diseases. We are also trying to create artificial machines. We can actually use it in the microscopic and nanoscopic level. So I would like, if you are interested to come across, we will happy to chat and engage on this for further.
Professor Saran, he works on cancer, by the way. We often heard that biology is tricky, that biology is very difficult. Biology समझ में नहीं आती. बहुत कुछ है, बहुत कुछ सीखना पड़ता है. This particular video seemed very beautiful and very choreographed and almost like a dance, Which is the choreography that fascinates you the most? Which choreography do you find the most, I guess, dangerous from a cancer?
Thanks, Arath. So again, good evening to everybody. Really special thanks to all of you because it's I know weekend and you guys are here, so I understand the interest and that you have to pursue or postgrad or PhD. So I'm Professor Saran Kumar, working since 4 years at IIT Delhi in Kusuma School of Biological Sciences. So we have different wings, as you would see. And coming to the my main core area of work is mainly cancer biology. That is what I am interested in, to understand what happens and how it happens, and if we can design better cure for the same. Coming to your question, Arath, yes, specifically, biology is always called as a science of exceptions. Biology is also, when you said messiness, I wouldn't call it a messiness, but it's definitely there is a method behind this messiness. How much do we know? Still very little. There is a lot to be known. That's why I would, if I have to give an analogy of a small kid playing, right? वो usually Legos is the craze, right? So let's say उसमें लिखा होता है कि 6+, right? So if you give it to a 4+ kid, he will think that this is too complex. Just don't bring it near me. But if you give it to the 8+ or 6+ kid, he would explore it and he will relish it, and the one who will never sit on it will be able to understand. Similarly, with respect to biology, there are few techniques which are still naive and we need to improve that to understand what is happening. We have understood so much, but still there are a lot of variations, and every one of you are unique, right? So every one of you have a different biology, but everybody is having 46 chromosomes almost. Again, science of exception. That's why I always say almost everybody. So even though it is all the same, the exact number of, let's say, 3 billion bases that you have, but still every one of you are unique. So these are the things which we learn in our department. If Arath, I may take 2 more minutes, just would like to brief you about also Kusuma School of Biological Sciences, because I see, prospective postgrads or PhD students. So we have almost 100+ PhD students now. And we have also opened up a master's in biological sciences. This is a new course, which I can confidently say that this is one in India which has practical component in each of the subject that we teach. In all the subjects that you learn, there is a practical component, because we really believe that lab exposure or really what is required in the current society or to understand biology, that is what we are trying to give it to the students. And I think that is one thing which should really interest you all. Yeah, thank you so much.
Thanks so much, Professor Saran. Um, so, there are these are nano robots, by the way, that I found on a video in YouTube. And you can see that, they've been introduced into the bloodstream, and this is really how the future of drug delivery stands, right? In addition to a lot of these biorobots, there's also a lot of, this is all cool, right? There are these nano robots. I showed you a cockroach which you can control with an iPhone. You've seen beautiful nanoscale machines. But in a country like India, the cost of your device, the last person availability is crucial, right? जो भी हम बनाते हैं, जो भी हम लैब में देखते हैं, वो उसको आखिरी गांव तक जाना चाहिए, किसी को एक्चुअली फायदा होना चाहिए, right? And so it is in this question that really we have a researcher like Professor Varun over here who can help us answer these questions. कि जो जितना भी amazing research Professor Langovan, Professor Saran और मेरे जैसे लोग करते हैं, वो प्रोफेसर वरुण जैसे साइंटिस्ट्स एक्चुअली आखिरी पर्सन तक पहुंचाने में वो द रिसर्च इज ऑपरेशंस रिसर्च, सो ही हेल्प्स अस ऑप्टिमाइज द रूट टू गेट टू दैट लास्ट पर्सन. So Professor Varun, how do you ensure that something that say Professor Langovan does actually reaches the most far-flung village in India?
Right. So thank you very much for that question, and of course for organizing this session. So I'm happy to be here. So there is of course the question of developing technology itself, right? And then there is of course the question of, as I think Professor Kalra put it, the access to the technology, right? And if you, and of course I think one of the questions that fundamentally I think occur to all of us when we talk about medical technology, of course, is that the majority, and I know this because I've heard this from many doctors, both in private institutions, private hospitals, public institutions such as AIIMS, is that the majority of the the majority of the medical devices, the implants, all the technology that we use at this point right now is actually imported, right? So there is a huge scope in terms of the research that, for example, Professor Langovan is working on or Professor Saran is working on to, of course, indigenously come up with lower cost alternatives to this, to the imported technology that we use. And so that the moment that you make it in India, that the cost drops by a factor of at least 50%, I should say, right? Likely much more. So once, let's say, the technology itself is developed, then there is a question of actually access, right? So if you look at, for example, the West, right? Or let's say a lot of, when I say West, I mean the US, Western Europe, North America to some extent, some parts of Australasia, Asia Pacific, all of those regions. So the way people access care is somewhat straightforward. There are still a lot of intricacies around, of course, the systems that are actually present, but largely there is a clear sort of straight line. For example, in the US, it is through insurance. If you go to Western Europe and Australasia and Asia Pacific regions, usually the government mediates access to care, right? So you don't pay at the point of care, it comes from the taxes in some sense. So in the Indian context, it is a little bit of a mess, right? So you have out-of-pocket care, you have, for example, you can just walk into a clinic and just pay for your consultation. You can just walk into a hospital, for example, and pay for your consultation if you're able to, if it's a private, if it's a private hospital. If it's a public hospital, like for example, AIIMS or Safdarjung, then you don't pay for the services, but you pay for consumables in some, right? So the question of, and then on top of that, of course, the government has something called as a national list of essential medicines, right? Which regulates the price of things like insulin, for example, certain cancer drugs, certain, for example, like heart disease drugs and all of that. So there are a lot of questions around here about, can we systematically analyze this system using mathematical or computational methods, right? Can we come up with a framework with which we can actually figure out what is the minimum price or the maximum price that I think a particular medical technology, let's say, for example, something that two of my colleagues here, let's say, for example, they develop, what should be the maximum price that that you should assign to that technology, right? Based on some notion of, let's say, maximizing social welfare in some sense, right? And this is something that is done in the West. It is done in Western Europe. Wherever there is, I think, a relatively, for example, straightforward way of accessing care, that is there. So the development of this in the Indian context, although there is some progress towards it, it's largely an open question. And this is a fundamentally a mathematically and a mathematical computational question, actually. And this is the sort of thing that we're working on. How do you mediate access to essentially this sort of care, right? Yeah.
So thank you for all of your answers. I'll tell you a little bit all about myself as well. Okay. So I work in the Center for Biomedical Engineering, right? My undergraduate degree is actually a BSc, and my BSc is in chemistry. Okay, so chemistry. But my MSc is in biology, and my PhD is in physics. ठीक है? और मैं professor हूँ biomedical engineering में. ठीक है? So the point I'm trying to say is maybe we can just go around the room and just see. And I bet you everybody will have an undergrad in different things. ठीक है? आपका undergrad किस field में है sir?
Biochemical engineering.
Mine is in production engineering.
So chemistry, biochemical engineering, production engineering,
Biotechnology.
there you go. So if you think that healthcare technology is only for biologists, that is not true. Just look at this stage. All of us are coming from completely different backgrounds, right? I am in the department of biomedical engineering, biochemical engineering and biotechnology, mechanical engineering, and biological sciences. And if that isn't the best reason to do healthcare technologies, then I don't know what is. Okay? So with this, we thank you for your attention. It's 3:15. We said we take only half an hour of yours, and that's what we've done.
Thank you so much.
Okay, so after that very interesting conversation about healthcare, which in line with Anveshan's philosophy of trying to bring different academic units together under different themes, we have the next thematic session now, which is titled Advanced Materials, Mechanics, and Quantum Technologies, very much in line with one of the thrust areas of the institution. And just like the previous session, this is going to be slightly different. We are going to have different talks by different faculty members instead of a panel discussion, but it will largely be in similar spirit. And the faculty members who would be part of this thematic session are Professor Saswata Bhattacharya from the Department of Physics, Professor Rohit Malik from the Department of Material Sciences and Engineering, Professor Malloy K. Singha from the Department of Applied Mechanics, Professor Manjesh Kumar from the Department of Chemical Engineering, and Professor Sajesh P. Thomas from the Department of Chemistry. Professor Sajesh P. Thomas is going to moderate the session. So, Professor Sajesh, maybe you can take it forward. Thank you.
I'm Dr. Sajesh Thomas from Department of Chemistry. So we're going to have a session on materials, and we have a line of speakers. I'm also listed as one of the speakers, but for the interest of time, I'll skip that part. And we're going to talk about materials. So I'll request the speakers to keep the talk to 8 minutes, and the remaining 2 minutes, at the end, we'll have a interaction section with the students. So yeah, that's it. So we'll start with Professor Shashwata Bhattacharya from Department of Physics, and this will be followed by another talk by Professor Malloy Singha from Department of Applied Mechanics. So the broad theme is materials, and just before the first talk starts, we have a material research going on in chemistry department, in physics department, and we have a dedicated Department of Material Science and Engineering department in IIT Delhi. So different angles from which we look at new materials and discover new materials. We hope this session will give you some idea about it. So with that, I invite the next speaker.
Quantum material, it's a heavy thing. That's why it's taking time to get load. Well, anyway, so I belong from physics department. Fortunately or unfortunately, I did BSc physics, MSc physics, PhD physics, postdoc physics, and in the department in physics still. So anyways, so just broadly to tell you what we are doing in the department. So first, it's a little bit confusing that when we call advanced material, when we call quantum material, and when we call materials physics or materials chemistry. So we can distinguish it like this. So when something is giving very good advanced property, that we can put something bit higher than normal materials. And that's called sort of advanced materials. But all advanced materials, do you really need to call them quantum materials? The answer is no. Because as a theoretical physicist, if you want to understand that, I mean, in principle, you have to solve a Hamiltonian. If that Hamiltonian can be solvable using Schrodinger formation of quantum mechanics, that's okay. That's not quantum materials usually. But if you need to involve Dirac formalism, then we usually call those as quantum materials. So anyway, just broadly, this is the group I am leading in the Department of Physics. So we try to understand the correlation of electrons, the correlation of the electrons with presence of light, presence of other electrons, or in presence of symmetry of the materials. Now, I do not want to go to details of this methodology because this is not the venue here. We also try to discover materials using AI, but there is a separate session on AI, so I'm not going to touch upon that. But overall, we can tell you that this is what we are doing, that is sort of non-relativistic spintronics or altermagnetism, then topological valitronics or spin texture, quantum confined optoelectronics, and sustainable energy and thermal transport. These are what we do in my group. And of course, it is not possible to talk about everything in this particular talk. So if you are interested, you can take a snapshot of this. You can see these recent publications as well. I will briefly tell you what do I mean by non-relativistic spintronics or altermagnetism. That is also so-called very hot topic these days in the field of quantum materials. So we all know that usually earlier we had electronics. I mean, that is what it is. Precisely, if you want to understand electronics, that is exploiting electrons' charge degree of freedom, right? So you apply a potential and the electron keeps on moving, and sort of because of that, you are exploiting some property. But once you apply a potential, then there is a problem because it is not energy efficient. Also, there is a heat dissipation. That's why people come up with a very excellent idea that if you apply a very tiny magnetic field, electrons has other degrees of freedom, that is spin up or spin down, and then also you can align the electrons' motion alongside the way you want to do. And if you apply a very tiny magnetic field, that also sufficient to move the electrons, say either in the spin up channel or in the spin down channel. But that's how throughout whole decades, this new field that is evolved, that is called spintronics. And it is really very popular these days. All these mobile phones and all these devices, they all use this type of methodology. But there is a problem that is called spin dephasing. For example, suppose you have an up spin and it's moving, and then all on a sudden you have a material where you have impurity, it gets collided, and then since it does not have any memory, it is forgetting that whether it was an up spin or down spin. So if the spin is getting flipped, then earlier it was possibly contributing in the spin up channel, now it will contributing in the spin down channel. So that way, the get degraded. So this is a so-called Elliott-Allais dephasing. There are other dephasing techniques also. And also, these spintronics deals with materials which are usually heavy jet, because all you need to do is that you have to exploit the LS coupling. That is so-called spin orbit coupling. But can we do something better? The answer is yes. So if you want to do that, that's the concept that comes up. So this is basically the spintronics. So you use spin orbit coupling, is L dot S. So obviously if you want to get a high value of L dot S, you have to go for a L which is really high. That means d orbitals or f orbital or something like that. And if you see, these are typically materials like bismuth, then lead, thallium, arsenic. These are sometimes toxic also, not very easily available. And as a matter of fact, can we do something that I will get magnetism but without SOC? That's called non-relativistic spin splitting. And that is a very, very important discovery of this field. And that is like, if you want to play around with material symmetry, and if the symmetry is somehow broken, then also you get orbital angular momentum, that is L, and you can easily get L dot S out of that. And that's precisely not because of the spin orbit coupling. So what I'm going to do is that I'm going to introduce you another concept, which is called altermagnet. For example, all of you know what is ferromagnet. All of you possibly also know what is antiferromagnet. Both have certain pros and cons. For example, this ferromagnet materials spins are very much aligned. But the problem is that if you want to design a device where if you put a ferromagnetic material and if the device is also having a magnetic field, then this gets perturbed. That's not good. On the contrary, the antiferromagnets, they do not have inbuilt spin splitting. And as a matter of fact, they are also not very good. You have to either apply electric field or you have to do something so that you can get some spin splitting into the antiferromagnetic material. So can you really design a materials which is exploiting the behavior of, say, this type of materials like the spin splitting of ferromagnet, as well as you can exploit the non-spin nature like net spin moment 0 of these antiferromagnet materials. So that's our altermagnets. So let's now then up. So I have conventional electronics. My data carrier is charged. Heat dissipation is pretty high. Reliance on heavy element phasing. Now, then where you have spin plus SOC, and then heat dissipation is low, that's okay, but reliance on heavy element is high, and also spin dephasing is really high. And that's why I'm switching to this phase, which is another new field, which is called electronics. So earlier you had electronics, then you switch to spintronics, now you are moving towards twistronics. And you have spin, but without SOC, that is purely because of the crystal symmetry. I will show you in a minute. Then heat dissipation is ultra low, and reliance on heavy element, no, and spin dephasing risk is 0. So that's basically the new generation quantum technological materials that one needs to aim to synthesize. So how you do that? So you see here, this is a absolutely symmetric material, two-dimensional material, nice material, but spin channels are locked because of the symmetry. So what you need to do is that you have to do some engineering so that you can somehow break this symmetry, and as a matter of fact, this transport is getting unlocked. So there are 4 ways you can do that. Either you can twist, you can make strain, you can change the dimension from bulk to nano, you can do compositions of all these things. So we do all these 4 things in our group. If you are interested, you can see in this reference. I will just show you one example of this twistronics. So you see here, this is a sheet, and this is another sheet on top of that, and they are absolutely symmetric. No symmetry is broken. Now if you slightly twist like this, suppose with this angle, then this symmetry is completely broken, and the outcome is this. This is a layered kind of structure, antiferromagnetic structure, and you can clearly see that non-relativistic splitting is noted here. This equals strongest SOC-induced splitting in heavy elements, but is achieved purely through geometric rotation of abundant lightweight antiferromagnetic magnets. No SOC is involved. You can clearly understand that these are simple materials. There is no bismuth, there is no heavy element, or so on and so forth, but it shows excellent magnetic behavior. The other one is like this. Suppose if you can design a spin valve. For example, you have designed a altermagnets which is possibly showing G to I wave kind of altermagnets. And if you can do something so that you can reduce again the symmetry or break the symmetry, so that this becomes a different phase, as noted here. You can see here, this is the VVM, and the spin texture is like this. This is G wave altermagnets. The moment you apply a slight amount of 1% diagonal shear strain, you can clearly see D wave altermagnets, and the spin transport is very good. So you can think it as a device. In normal state, it is not conducting. It has transport property 0. You press it little bit or you apply a little bit of strain, this starts conducting. So the conclusion is this. So basically the era of relying on rare, heavy and toxic elements of quantum advancements is ending. By mastering the geometry of abundant materials, we can engineer the exact symmetry required for quantum control. That's exactly what we are doing. Engineered symmetry is the ultimate quantum materials. With this, I would just like to advertise my group and acknowledge my students who did all these calculations. And you see that this is also the scope of being here in IIT Delhi. You see all my PhD students are very well placed across the world, starting from MIT, Stanford, University of South Carolina, some of the leading institutes in Germany, in Trinity College Dublin, and so on and so forth. With this, thank you very much. If you have any questions, you can ask me.
Hello everyone. Am I audible? So thanks for joining us for this second edition of Anveshan. I'm Professor Rohit Malik from Material Science and Engineering Department. And today I will be briefing you about our department. We are quite a young department, only started in 2019. And currently we are a family of 400 members, including 22 faculty members. And talking about the QS ranking, we are standing at second position in material science and engineering subject. Now talking about the research in our department, we have 4 research verticals, including metal and ceramics, polymers, electronic and energy materials, and computational. So now I will go in slight detail of these 4 verticals. Okay, so talking about the first vertical, that is metal and ceramic research vertical. So I am also from this vertical. We are total of 8 faculties working in this vertical, and our research areas include mechanical behavior, engineered microstructure, thermomechanical processing, alloy design, lattice defect analysis, and surface engineering and tribology of metal and ceramic. Now moving on to the next research vertical in our department, that is polymer research vertical. So we have 6 faculties working in this research vertical, and here are some research areas on which they are working. So I would like to emphasize these are not the exhaustive areas. So I would encourage you to visit our department site for and visit the individual faculty profile for detailed research areas. So some of the research area in polymer research verticals are smart elastomeric materials, polymer matrix composite, tribology, mechanical behavior, 3D printing, membranes, energy materials, hybrid materials, and catalytic materials. Now moving on to the next vertical, that is electronic and energy material research vertical. So again, we have 4 faculty members working in this vertical, and some of their research interests include semiconductor, nanostructure and device applications, magnetic nanowire and magnetic tunnel junctions for spintronic device applications, MEMS and NEMS devices, solar cells, thermoelectric devices, energy harvesting materials. Now moving on to the final vertical. So our 4th vertical of our department is computational research vertical, and we have 4 faculty members working into this vertical, and some of their research interests include first principle material design, micromagnetic simulation, computational material chemistry, molecular modeling, and simulation of soft material. So I would encourage you to visit our site for details on the research area of each of our faculty members. And you are more than welcome to reach out to faculty members. You can even fix a offline meeting with them. So they would be more than happy to entertain your queries. Now I would like to briefly introduce my research group. So the name of my research group is Advanced Structural Ceramic Group. So we work on structural ceramic that are designed to bear mechanical loads, and they are supposed to operate under harsh conditions such as high temperature, wear corrosion, and thermal shock. So in structural ceramic, we are working on both fundamental and applied research aspects. We are currently working on additive manufacturing of ceramics, and in this we are working on two research topics. One of them is designing a novel class of material which are called metamaterials. Now this class of material is only possible through additive manufacturing, where we can design very unique structures which show a unique combination of property that is not conventionally found with conventional materials. For example, here you see a gyroid shape. So this kind of shape, it provides very high heat transfer and very high energy absorption. So this we have made using additive manufacturing. So this is one of the research area in my lab where we develop these materials with very unique properties and that are induced through a special design, special structure of these materials. And the second direction in case of additive manufacturing of ceramics in my lab is the microstructural engineering. Again, we are able to develop some very special kind of microstructures that are only possible with the additive manufacturing. For example, we were able to align these platelet shape of alumina grains in concentric tube-like fashion. And in the second image, you can see these are ceramic fibers. They have been homogeneously distributed and well aligned along certain direction in a ceramic matrix. Now, advantage of these kind of microstructure is that you can tune the mechanical behavior of this ceramic composite, and that is only possible through the additive manufacturing now. Now, moving on to the applied research aspect of my lab. So, structural ceramics, they're very critical material for the nuclear, aerospace, and defense industry. And currently, in our country, the nuclear industry is targeting for very high temperature reactors. And for that, they need high temperature materials. And in this regard, we are developing these, high temperature fuels, which are called fully micro-encapsulated fuels. They are based on silicon carbide material. Now, moving on to the defense and aerospace sector. So you know that our country is planning for a manned mission to moon. So currently we have the technology that we can take a person from here. But when we try to bring him back, there is an issue because of the atmospheric heating. It is not safe to bring that back to the shuttle back to the atmosphere. So we have to encounter intense atmospheric heating, and for that we need heat shields. So one of research direction in my lab is to also develop these kind of heat shields. Now the final, this SA micrograph, it shows a fiber reinforced ceramic matrix composite. Now these are the most advanced high temperature material that are currently used in aero engines. So this is also one of research direction in my lab where we are developing these materials for next generation of aircraft and aero engines. So that's a very brief idea of my lab. And talking about the academic programs in our department, so because you intend to do post-graduation, so we offer a Master of Technology degree in Material Science and Engineering with specialization in Polymer Science and Technology, and another specialization in Metal and Ceramics. We also offer a research-specific course that is called Master of Science with Research, MSR, in Material Science and Engineering, and also we do offer a PhD in Material Science and Engineering. And these are, some of, so far, our students, they have got, even faculty and staff scientist position in various prestigious institutions like IIT Palakkad and even IIT Delhi, IIT Patna, sorry. And many of our, PhD students, they have moved for postdoc in prestigious international universities. And many of them, they have moved to government and private sector as well. Okay, so that's it from my side. So if you have any queries, feel free to reach out to me or reach out to any faculty member of our department. So I would encourage you to visit our website where all the detailed information about all the faculty members is there. And if you wish to meet them, feel free to drop an email, and I think they would be more than happy to entertain your queries. So with that, thank you.
Hello, good morning everyone. I am Sasi. Now I am a project assistant in electronics department, Slide, Longwal, Sangrur, Punjab. I am working on design and development of suffer capsule endoscopic devices, which is for lows or biomedical.
Sorry, because of the echo, I am not
macro
able to hear you properly. Because of the echo, I am not able to. Yeah.
Okay, sorry. Basically, I am working on microstrip patch antenna sensor for capsule endoscopy. So, sir, my question is that how can material properties improve performance of antenna sensor?
Okay,
Antenna
so
sensor.
I am working in structural ceramic. So I'm afraid I am not the right guy to answer that question. But we have faculty working in energy and electronics materials. So I think they are the best people to answer your queries. So we can meet after this, and I can share the contact with you. So they should be able to answer, question related to the functional materials. So I work on structural materials.
Thank you.
Yeah.
Good afternoon, everyone. Am I audible? Okay. So I am Malay Singh from Applied Mechanics Department. Today I am here to introduce our department to you. So we have in our Applied Mechanics Department, we have a BTech program, we have a MTech program, and we also have MSR and PhD program. So one unique extra program we do have, that is the postgraduate diploma course in the naval construction. This is only for Indian Navy. Indian naval officers with graduation comes to us to learn something related to their ship dynamics, because our core strength is the mechanics. So we teach engineering mechanics, solid mechanics, fluid mechanics, and data-driven mechanics, and experimental methods for solids and fluids. If you see, this is our student strength. We have at present around 106 PhD students and 68 MTech students. We have BTech students 164. So these are our faculty members. So we have basically two groups. One is solid mechanics and one is the fluid mechanics. So all of us is working on solid mechanics, and many faculty members are working on fluid mechanics. And because of our PGDIT program, we have 3 naval officers who are working as a faculty, adjunct faculty. So they teach the courses exactly related to Navy, whereas we teach their basic fundamentals on the mechanics, solid mechanics and fluid mechanics. So then these are our research areas. So because basically we have 2 groups. So solid mechanics group, we work on composite materials, and then stability dynamics, continuum damage mechanics, fatigue, fracture, failure, and structural health monitoring, multi-scale mechanics, and biomechanics, soft robotics, machine learning. Similarly, the fluids group is working on hydrodynamic stability, turbulent flows modeling, complex fluid flows, and several others like hypersonic flows and flow diagnostic. So with this background, I want to give you next 5 minutes, I want to give you a brief idea of what our research students are doing. Basically, our core strength since our core strength is mechanics, so mechanics is of materials is applicable to different fields of engineering, like civil engineering, naval construction, aerospace engineering, mechanical engineering, any biomechanics, or even material science for some computation. So here, so this slide, I want to show you that this is an aluminum plate. We are loading under pure shear, shear. This is a special setup for that. And once, and this is the image we have taken using the digital image correlation. And what we get, this material can take a load under shear strain of up to 80 MPa. After that, the material fails due to plasticity and other failure. Now, the same material we have loaded under dynamic tension. So when we are loading under dynamic tension, we can see the material can take around 150. But as what happens, this material, if we load it very fast rate, like impact or blast or shock kind of event, then the material behavior changes. So this is a particular setup. This is called John Hopkinson pressure bar. So using the Hopkinson pressure bar, we can get the material behavior at different loads of different rates of loading. So normal static loading and like impact or shock wave or blast loading, those are different. So accordingly, we can characterize the materials. Next is my different colleagues are working in different types of material, like composite material. Some are working on the functional grade material. Some are working on metamaterials and carbon nanotube or nanomechanics. Some are working even on continuum damage mechanics, strain gradient plasticity, fatigue modeling, molecular dynamics, DFT, digital twin framework, uncertainty quantification. So different colleagues, I have shown you their our photograph. They are working on different aspects of it. Even someone of us is working on the on sandwich panels made of the sandwich panel, top and bottom. We can have a plate like aluminum plate, whereas the core, the middle core, can be sandwich made of sandwich materials. So, and we have a impact mechanics laboratory where we have a facility to test any specimen, like here a circular plate, aluminum plate is tested under impact of 135 meter per second with a hemispherical projectile, and I'm showing you the DIC image of the perforation. Similarly, we have a biomechanics group, those who are working on biomechanics and soft robotics. This is a picture. I'm showing the fracture in pine wood. So since pine wood is anisotropic and brittle, so the crack propagation is sudden. So this kind of works we are doing. And another thing is the stability and dynamics problem. So this figure shows you that this is a numerical simulation using the finite element method. We are showing that how amplitude increases with change in the forcing frequency. And next figure, I'm showing you how a panel or a structure can be dynamically unstable. Like here, a shear panel is there. A shear panel is loaded under a dynamic load. So we can see that at multiple modes may get excited at the same time. And we have also a group who is working on this on structural health monitoring. This is actually an effort to detect the damage without reaching into the structure or without any further damage. What we do, if we just pass a signal or some kinds of wave from one end, if we actuate at one end and get the response of the signal on the other hand. So healthy structures gives us a different signal, whereas the defect structure gives a different signal. From the signal, we can just locate the damage. And then one more group is working on the drag reduction in ship, whereas we have a water tunnel facility. Along with, we have a very good team who is working on the computational fluid dynamics problem, where we are trying to reduce the drag in the ship. And then we have also trying to reduce the noise reduction in the drone. So we have 3D printer, so we can print the propeller. Basically, it depends on the propeller, and it depends. And so we have done some shape optimization, some of my colleagues, and we're trying to reduce the drone noise. Similarly, we have several wind tunnels with several capacities. So where we can experimentally simulate the boundary layer layers, and also together with the fluid structure interaction action software like CFD, we are studying the high speed and low speed aerodynamics. And we have have an ongoing project on the vertical axis wind turbine. We are trying to increase the efficiency of the vertical axis wind turbines. So, and last slide. So this is a recently developed underwater vehicle from our department. So you can see that this is the underwater. This water vehicle is designed and it is working in a swimming pool properly. So with this, I am just finishing my presentation. So this is overall. I have only presented few works of our department. So if anyone is interested in any mechanics related problems, you can please contact any one of us in the department.
Okay, thank you, sir. For the interest of time, we will keep the questions towards the end of the session. Next, I will invite Professor Manjesh Kumar from Department of Chemical Engineering.
So I will talk about some of the things that we do in the Department of Chemical Engineering, and most of the things that I will talk about will be pertaining to the material, but there is a wide scope that a lot of people are working in various aspects of chemical engineering. But mostly this time, just because of the material division, I will talk about the various kind of material that we work upon. So if you look at the modern lifestyle itself, like there is a lot of material that you encounter. So there can be energy and environment related material. Think about the battery, fuel cell, electrolyzer, catalyst, adsorbent, fuels, emissions, and quantum material. These are various things that you face every day. A lot of faculties are working on various aspects of these things. If you look at the modern lifestyle, you have fine chemicals, bioplastic, polymers, right? Various faculty work on those aspects of the problems. Similarly, biomolecular systems. So you heard biotechnology and all. Chemical engineering department also works on various kind of diagnostic and biotherapeutics kind of system, right? So you connect with the various faculties working on various kind of material of interest. Just to give you a quick example, if you look at your life from morning till evening itself, you will come across various kind of material. And believe me, in every aspect of this, chemical engineers are involved. So take a quick route. You start with the 7K toothpaste, soaps, cosmetics, transport fuel, catalytic converter, RO, everywhere. All these materials, chemical engineering plays a significant role, and all these are some kind of material design itself, right? And you will find people working on and solving some of these problems, right? The idea is you don't realize it, we don't realize it, but if you look at the scope, it's huge and it affects our life every day from morning till evening. So yeah, and some of the problem that we will solving through these things is a food, energy, environment, and being in Delhi, So first thing that comes to us, so let's look at the bigger problem of sustainability, right? That's the most talked about things, but why there is a problem, right? The idea is India is growing, we want to be a developed nation, and to be a developed nation, we have to have lots of resources, right? So one thing we know, our population is increasing, you want jobs after that. For sure, to have the developed nation, you need power, because you need electricity at your home. You need cements and iron and steel to build new homes, right? All these things require manufacturing. But when you do manufacturing, there is CO2 and global warming. You are in a catch-22 situation, right? The idea is we have to work on consuming or removing those CO2. And there are various methodologies. I will not get you into the details, but there are processes like electrochemical, photochemical, thermochemical. These processes exist where you need to design various kind of material so that you can consume CO2 and convert into useful product. So lots of faculties in our department work in this bigger umbrella of sustainability, right? So to give you an example, simple CO2 can have various pathways and I can convert into very value-added products. Now, it will not happen in a day. Just simply I ask the CO2 to convert itself. It will not do. I need to design a special kind of materials, catalytic material to do this function. And for that, you will see a lot of faculty work on various kind of material like perovskite, MOF, zeolites, metal oxide. All these things are used in industry to convert these things. So if you want to work in these kind of problems, you should consult many faculties who are working on these larger problems. To give you an example, say consortium of faculty are working on converting the CO2 into methanol. And what we are trying to develop is pilot plant with our industrial partner Thermex and funding from the DST. This is a large consortium project where we want to develop the pilot plant where we can convert the CO2 into methanol, which is a useful product. So one thing you should realize, lot of faculty works in group. Any larger problem, think about the plant. I cannot solve it. I don't know about everything. Some part I know, some part other faculty know, or what happens, multiple faculty come together to solve a bigger problem. If we have some idea about this, you want to work on these bigger problems, you should connect with us. Think about refinery. Chemical engineering, if you say, simple idea that comes to your brain is refinery, right? You see big towers. You know, one reactor, the height of reactor is equivalent to 3-story building. Like if you see the FCC unit. If you zoom into it, inside that we use catalyst. If you further zoom into it, that catalyst is made of various other things. We call zeolite, metal, clay, binders, all these things. And if we have to work on those catalytic material, it's a chemical engineer who works on these domains. Now the interesting part, somebody said it is the hair thickness that you can see. But most of the catalysts we make is in micron and many in nanometers. So the idea is most of the reaction in big refinery that you are seeing is not actually happening at such a high length and scale and volume. Actual reactions are happening in nanometer scale. So you need to know about that. So if you are interested in solving the problem of refinery and design a material for that, again, chemical engineering is the right place to go ahead with that. I tell you another example. Being in Delhi, one thing you know about BS6 and BS4. Like what is the basic difference? Can anybody tell me what is the difference between a car which is BS4 and a car which is BS6? क्यों पैसा दे रहे हो ज़्यादा for buying a BS6 car? See, and government is the government stupid that they are implementing a stricter policy and asking you to buy a new car? That's not the case. What happens? BS4 gives more pollutant, BS6 gives less pollutant. For that, we have to use a special kind of catalytic converter. But then how does it work? If you look at it, at the bottom of your car in truck, you will see catalytic converter. You zoom into it, you will see this kind of a structure. You further zoom into it, you see that kind of monolith structure. You zoom into it, you see another kind of deposit. The deposit that you are seeing, you zoom into that. That is the catalyst that catalytic converter is using, and is the chemical engineer that designed these kind of catalytic material to remove the impurities from your engines, right? So the idea that, and if you zoom onto even on the surface of that, you will see nice structures. So the idea is that these things are happening at molecular scale. We are converting these NOx, SOx using catalytic converter. For those problems, we work onto that. Why do we do all this? For simple reason, to keep you healthy. There is a picture from Dr. Trihan. If you have the lungs from Himachal, I have intentionally made it less transparent so that it does not look gold to you. The idea is Himachal lungs is cleaner than the lung from the Delhi, just because of the pollution. So we have to look at the larger problems that we are trying to solve. Another big thing that you hear every day is about batteries, fuel cell, because we have to talk about hydrogen, we have to talk about cleaner technology, right? So a lot of faculties are working on designing batteries, but battery, what you see at your home is the large, it's a collection of various items. It requires various kind of electrode material. Who will design those electrode material? We design work on those electrode material so that my battery can go for longer period. I can convert some of the material using those electrolyzers, right? So you can either make the PEM cell, fuel cell, microfluidic fuel cell, or other kind of solid oxide fuel cell. These are the various kind of battery and fuel cell that is used for either chemical conversion, which will help you energy storage, or providing the energy. But who will design the battery? So we have a lot of faculties who work on these things. And it doesn't happen so easily. You have to design the devices. If I know that I have to make a battery, I have to design devices at various scales, and in devices you have to particularly work on the material part of it. And that becomes, so whenever I show you this, it looks fancy to you, right? Ki batteries are this, but actual problem lies in designing those materials, and that is at molecular scale. So that might seem boring to you, but that is where the problem lies. That's what you need to solve. I cannot just impress you by saying the larger picture, but when you are in the lab, you have to work on. So, and to do that, again, we have a cluster of faculty, we have a center of excellence, we are designing various kind of new battery material, new fuel cell material to improve the efficiency of that. Again, I will not bore you with all the details, but actually, it's good to look at, hey, you want to buy a good battery, you want to get a good battery, but without working, you cannot get it. Somebody has to work in the lab to design a better battery and earn the premium on that, right? So there's a lot of technical information required. Once you join the lab, you start going through those things. Last two aspects of it, so think about the infectious diseases, right? So many times, that bacteria attack us, that get attached to our cell, we feel sick, and then we have the infection. But what do you do? To find out those things, you go to either some diagnostic, you give the blood sample, but then how do they measure it? How do they know that you got this infection? They need a device for that. Or once you know that, they need to supplement with some pharmaceutical molecule. To understand, to make those devices, again you need material. So for example, some faculty works on designing silver nanoparticle or various other kind of nanoparticles that are used along with light sources, which have the greater susceptibility to particular bacteria, and then you can biosense that, oh, you got infected with these kind of bacteria. So again, it requires designing a material sensor which requires certain kind of material and hence dealing with it, right? Similarly, you already know about the quantum material. This is last portion. You already know about the quantum material and semiconductors. You already know things have become really, really small. Now silicon might be phasing out, newer material will be emerging, right? Which requires at the atomic scale kind of synthesis, right? So for that, there are a group of at least we have a faculty which is working on new kind of material called bismuth oxysilane, again, for the newer devices, newer quantum devices, right? So to give you an example, they are designing, growing particular kind of quantum material. They are making devices using those films and then try to check various electronic properties. All these things require growth and understanding at the molecular scale. So these are the broad strokes. And for doing that, we need facility. We have those facility. You can visit us anytime. And this is the last slide for like a quiz. So there are three things you are looking at. First one is turtle, and that is the actual hand. That's the hand of my wife, and that is the real turtle from Mauritius. Second one, you are looking at kidney stone. And third one, the powder that you are looking at is the powder that gets deposited in catalytic converter. If I ask you what is common between all three of these, can you tell me? Sorry? Calcium carbonate, but not in catalytic converter. That is silica alumina. Do you think these are different problems? Because there is one is kidney stone, one is turtle, one is catalytic converter. If you look at the molecular scale, very frankly, you will see all these things. If you start imaging the surface of these material, all these look like a helical structure. How these material form, nature makes these in an almost similar way, with some variation here and there. But if you look just with the naked eye, you will never find it, right? To understand that, you need to do research, you need to get at the molecular scale, which you need to have the higher, and then only you can really come up with the innovative solution, right? And if I show you the video of that, sorry, let me see. Helicox that you see, actually in your kidney stone that process is happening. It's just that you see like a stone, but it's molecular calcium carbonate which is depositing slowly and that is forming. If you have to find a solution to that, you have to stop this growth. Right? So you have to understand everything start merging, but you have to come with a diagnostic to solve all this problem. With that, I will close my talk, but we welcome you in the Department of Chemical Engineering. If you want to learn more, please talk to us. Thank you so much for your time.
We are moving towards the end of this session. I think we have heard from the perspective of a physicist and applied mechanics view, as well as material scientist and chemical engineer. I'm a chemist. I'm from the Department of Chemistry. Supposed to talk about what we do in terms of materials, but we have people working in nanochemistry, nanomaterials. Professor Soumik Siddhanta is here. I work on crystalline materials, soft materials, and we have colleagues, faculty colleagues working on battery materials. So we will talk about it has to start from atoms together to make materials. So it has to start from chemistry, I would say. But to understand them, you would need physics, you would need material characterization, and structural engineering. We heard about it. So you may not have understood everything that you heard now, which is okay. But the idea is to get an overall flavor of this, so that if you want to know more about them, you can directly approach us and ask your questions.
Back with the faculty members, as the different chairs have mentioned. And now we have the last thematic session, which will be back to conversations. And that session is titled Digital Frontiers and Communication, Artificial Intelligence, Data, Supercomputing, and Quantum Computing. And we will have a panel discussion mode. We have the following faculty members to join us. Professor Sudipan Saha from the Yardley School of Artificial Intelligence. Professor Bhaskar Mukhoti, also from the School of Artificial Intelligence. Professor Neelkant Kundu from the Center for Applied Research in Electronics. And Professor Gokulnath from the Bharati School of Information Technology and jointly with the Center for Automotive Research and Tribology. Professor Sudipan Saha is going to moderate the session. After Professor Sudipan, please.
We have Professor Bhaskar Mukhoti, also from Yardley School of AI, Professor Kundu from KIAR, right? And also Professor Gokulnath from CARD, right? Okay. So before starting this session, I think it's important to understand a bit of history, right? So how many of you are actually from computer science or electronics and telecommunication or this kind of like mathematics, this kind of background here? Okay, great. Quite a lot of you, right? In any case, I mean, the stories that we are going to tell in this session that connects to the other branches also. So this connects to our society in general. So most of us, I mean, all four of us are like almost around of the same age. So in our, let's say around 2004, 5, 6, around that time we were teenager, or let's say like the late teenagers, right? And at that point of time, the first time the social media came to India. So how many of you have heard something like Orkut? Almost no one even heard its name, right? So yeah, exactly. So this is what started the social media in India as such. And why I'm talking about this, like, so I was like, let's say like I just completed my class 12 in 2007 or so. And for the first time, I got to know about this social media, Orkut, and I mean, before that, the idea was that, okay, I'm graduating from my like high school and all, and I will never be in touch with my friends anymore. Maybe like I may come across one or two in the later stages of my life, but I will lose my contact with most of them, right? However, that was not the case. And at the same time, talking about a bit also about the artificial intelligence. So how many of you have heard about something called LeNet? Did anyone hear it? LeNet? No one? So LeNet, the first CNN architecture was proposed as back as in 1999. However, what we see is that up to 2011, the convolutional neural network, okay, which actually revolutionized this AI era, like since in the 2010s decade, this was not popular as such. So what happened is that what stopped from the CNNs to become more popular is both from the hardware side, the GPU technology, and also the availability of the data. So data is one of the main point of today's session, right? So when I say data, I mean data like image, text, whatever, and like that it should be associated with some kind of label, right? Like an image, and let's say like an associated label is like a dog, cat, right? So when the ImageNet challenge, did any one of you hear about ImageNet challenge? So the ImageNet challenge, this was launched first time in the 2010. The winner was still the methods which were like based on the previous machine learning based methods like support vector machine. However, when the same challenge was again relaunched in 2011, by then the convolutional neural network was the winner. And since then, there is no looking back, you know. The first LeNet, the first architecture I'm talking about, this had, if I remember well, like about 60,000 or so parameters. Fast forward to 2011, the network which won the ImageNet challenge, AlexNet, this already had parameters in count in millions, okay? And over the decade, I will not bore you with the names of the architectures, however, over the decade, this parameter count keeps on increasing and increasing. In the image analysis domain, we keep on using the CNNs, whereas like there are other domains like text, the RNNs or the LSTMs were more popular. Until in 27, the language domain, they started adopting transformer, and eventually in the 2020, the computer vision domain also started adopting the transformers. And with the transformers, now the parameter count of the models, just imagine, like in the LeNet, I told that it was about 60,000, right? Now the parameter count is in the billions. And also, a bit of side story here. So when I was starting my own PhD in, I think most of you will concur with me, when I was starting my own PhD in 2016, so I was doing in one of the like really big lab in Europe. Despite being one of the really big lab in Europe, that particular research group did not have, with the point of time that I joined, this research group did not have a single GPU. By the time I graduated in 2020, okay, they had already about more than 10. The postdoc lab I joined had, let's say, in 2020, I'm talking about, in the middle of the COVID, they had like about 30 GPUs or so. I was really happy, you know, like they already have 30 GPUs. And now, let me share you with the good news. When we are talking right now, I mean, this month or these weeks only, like it has been made to the IIT Delhi community, a HPC cluster, which consists of 450, 100 GPUs, which has the compute capability of 250 AI petaflop. Okay, so this is the evolution that we have gone through. So 2016, I'm talking about in one of the big European lab, 0 GPUs, and now in IIT Delhi we have this cluster, which is 450 GPUs and 100 GPUs. Okay, so with all this, of course, comes a lot of questions. So it's not just okay, the things have gone just on the positive direction. Also at the same time, we see a lot of misuse of AI. So one of the persons in US who was assassinated like a few months back, I will not take the name, but most of you can guess. And the person was from a particular political ideology, let's say. that doesn't matter. However, when that person was assassinated, there were like videos circulated in this person's name that this person was speaking those things to justify the killing, you know. Later, it was debunked that, okay, most of those videos were created by deepfake, okay. At the same time, of course, the data and the communication, that also a very important aspect. And in the same time, one of the other dimension where we are seeing like very interesting progress is the quantum technology. So with the quantum technology, progress of the quantum technology, the existing cryptography protocols and all, they're becoming increasingly obsolete and replaced by the new cryptography protocols. So this is all that forms the background of today's session. And with this, I will invite first Professor Nilkant Kundu from CARE, Center for Applied Electronics.
Yeah, okay, so my research is the intersection of quantum information technology and communication systems. So basically, what is quantum computing? So technology which we are using today is the result of the first quantum revolution, where average or the bulk properties of quantum mechanics were used to develop these semiconductors, lasers, which are the backbone of today's information technology. And now we are moving to the second quantum revolution, basically where we are able to engineer single photons, atoms, and electrons to develop new information technologies which have capabilities far beyond that of the classical counterparts. And this opens up a lot of new challenges and a lot of new applications. That is the focus of my current research. And particularly, this quantum computing is based on the fundamental computing aspect of qubits, which, unlike classical bits, uses the principle of superposition and entanglement, so that it can simultaneously be in the superposition of 0 and 1, and upon measurement, it collapses to one of these states. And so basically, quantum algorithms use these principles to solve certain problems with exponentially fast complexity as compared to the classical algorithms. For example, the Shor's factoring algorithm, it can factorize a large number into its prime factors, and this basically brings a threat to our current encryption scheme. So basically, this RSA public key encryption, which is the backbone of our classical internet and our communication, that can be broken by quantum computers. When we have a fault tolerant quantum computer, these algorithms can be used to break them. So quantum computing is bringing a threat, and simultaneously we can use another quantum technology, which is quantum communication or quantum key distribution, which uses the fundamental principles of quantum mechanics to distribute perfectly secure keys. And once these keys are distributed, then they can be used for our encryption of the classical data, and it will provide unconditional information theoretic security. So apart from QKD, we can also improve the data capacity or the rates of our classical communication networks by using the quantum principles in the encoding and decoding of data, so that we can achieve higher capacity as compared to the classical Shannon capacity limit. Furthermore, with quantum communication, we can link between different quantum processors so that we can improve their overall computational capability, and they can solve much harder problems. And then is the application of quantum computing. So quantum computing has a lot of applications in AI, so it can accelerate some of these heavy computational tasks in AI by using these variational quantum circuits and quantum kernels. They help us in better feature representation in high dimensional Hilbert spaces. And they are currently being explored to see how quantum blocks or hybrid quantum machine learning models can solve some of our classical machine learning problems in a more efficient way. These are some of the research problems which are open in today's world. And quantum computing algorithms and quantum machine learning also has applications in optimizing our future wireless communication networks. So we are working on these domain where we are exploring how quantum algorithms and quantum enhanced signal processing can improve the physical layer signal processing problems in wireless communication and networks. And third is in the thing where quantum sensors are being used to measure some physical quantity, for example, temperature, electric field, magnetic field, or timing things with very high precision and accuracy as compared to the classical sensors. And this quantum sensors also has a lot of applications, for example, timing synchronization, which can ultimately lead to the improvement in our GPS localization accuracy as compared to the current GPS which we are using. Furthermore, we can use quantum enhanced localization for improved localization of targets. And also there is this emerging area of quantum radars and LiDAR, which basically uses this the unique quantum resource, which is the quantum entanglement, to have a better detection and ranging capability as compared to the classical radars. So this is a very new and emerging area, and it is an interdisciplinary research area which requires expertise from physics, electrical engineering, computer science, mathematics, and this is quite exciting. So basically, you don't need to be an expert in physics to work in this emerging area, and there's a lot of open problems to be solved in this domain. And yeah, so if you're excited about quantum information technology, quantum communications, you can join us at the Center for Applied Research in Electronics, and also Bharati School of Telecommunication Technology, where our group is working on some of these pressing problems from the quantum information perspective. And yeah, that's all from my side.
Thank you, Professor Nilkant. We'll take questions from the audience after we are done with all the speakers. But before moving on to the next speaker, I would also like to mention, before I forget, that Professor Nilkant is probably one of the first faculty members who is also offering a course on quantum machine learning. I guess it's not just something new for IIT Delhi, it's probably one of the first time in India itself. So that's one reason probably you would like to, stick to his research group. So now I will invite Professor Bhaskar Prati Mukhoti to talk on responsible AI.
Okay. So I would like to start with a simple thought experiment. For example, it was introduced in 2003, but I would like to hear from the audience what they have to say. Say, for example, at some point of time, we have some robots which we can instruct with some goals, and we tell the robot to collect paper clips, right? That is a simple instruction that we give to the robot, right? Which you think is intelligent, we believe is intelligent. So what do you think would be the consequence of this? If we just instruct it that the robot has to collect paper clips, and they can take actions depending on their intelligence. So if they are really intelligent, what they would do? Any ideas are open, like we want to open up a bit. So I would like to hear from the audience as well.
There is no volunteer, we'll just speak some.
Okay, so if there is no volunteer, then probably one of the panelists can answer if they like. No? Okay, so let me answer that if there is no answer from the audience. So because you just have mentioned that they have to collect the paper clips, right? So it would optimize only that, right? And nothing else. So that means it can collect all the metals around it, right? And collect the paper clips, right? Probably it can also take human beings and take all the material iron that is there from the body, right? And they can probably kill human beings so that the other activities are stopped, and it can optimize the paperclip collection, right? So why this weird consequence? Because when we say to a machine that you have to collect paper clips, right? We never mentioned that it has to protect human beings, it has to protect our interest, it has to maintain the environment, nothing else, right? So we just, so the consequence is that it would optimize everything else towards this, right? So this is a thought experiment introduced by Nick Bostrom. You can search in the internet. It sounds weird, but it is real. It is real in this sense that whenever you have an AI system and you optimize it for something, right? You solve some purpose with it. Things open. You don't mention about many other things, right? You just assume that it will do the other things on its own, right? So for example, you tell a car to drive from one place to another place, a robot, suppose. So you many things that it should not kill someone. Probably you are at least telling that, okay, it should kill someone, but you are making many things unspecified, right? Which as a human being, we are trained from our childhood that what we should do, what we should not.
Yeah,
So-
Professor Bhaskar,
Yes,
if I may add. So that's why we should not refer the cars as autonomous vehicle. We should refer it as automated vehicle. So if you call it as autonomous, so it has its own mind, you know. So you don't have to give any instruction. You just sit and it thinks, okay, let's go to the beach, and it goes on its own. So that's what the difference between autonomous and automated. So people always refer as autonomous vehicle, but we should refer it as automated vehicle, just to follow. Yeah.
So this is a broad problem in AI, where we call it an alignment problem. So alignment is that we are humans and we have some values inbuilt in us, but then there are robots, right, which are not humans, and we optimize them for some purpose. So how do we ensure that these robots will align the value of humans and they would do as expected even in an unspecified situation, which we have not specified yet? And this entire thing comes under, you can call, trustworthy machine learning or responsible AI, and alignment is one such problem. And there are many such open issues which we would be at a research level we have started with, right? But as AI progresses, these issues will be more vivid and we have to handle a lot of them, right? This comes, so I gave one of the example, but you can think of many such examples, right? So with like to conclude, if there is no further question.
We'll take the questions later. Now, I will invite Professor Gokulnath Thandabarayan from Center for Automotive Research, right? As he emphasized the difference between automated and so he will be speaking on intelligent transportation systems.
Yeah, thank you very much for the opportunity and good evening for everyone. I just asked this person to open my presentation. I think he's meddling with the phone. Excuse me.
Hi, Mr. Volunteer.
Yeah, he's very busy with the phone. Okay, anyways, so my name is Dr. Gokulnath, and I'm an assistant professor in the Center for Automotive Research, where people focus on developing automated vehicles, focusing on the battery side, the material side, the motor side, and I focus on the connectivity and autonomous vehicle as well. And I'm also part of Bharati, where I also focus on conducting research on communication part, how we can enable the vehicle and the drones and other vehicles to connect with each other in order to improve safety and efficiency. So please give me. So I will talk very abstract, not going into very detail, and keep my presentation very short. Yeah. So professors here talk about the responsible AI, the quantum computing, and Sudipan is a very well-known researcher in vision, so which focus on perception and sensing. So I want to conclude this talk by asking a big question. So these are all different core verticals. So, but where can we apply all these different verticals in a very real-time application? So it can be applied on health, it can be applied on smart cities, or it can be applied on transportation. So since I work in the transportation department, I have asked to talk about intelligent transportation systems. So let's focus on how we can apply these three different verticals in the transportation domain in order to improve safety and efficiency. So let's talk about the advancement in automated vehicles. There is a significant improvement in the technological advancement in automated vehicles, where different aspects such as vision, and different types of sensors has been incorporated, but still we have physical limitations. So whatever we apply AI in order to detect the environment, still adverse, the limitations such as adverse weather conditions and lightning and other factors could impact the sensing capabilities. As you can see from the second figure, which is obtained from the LiDAR sensor, an object in front of the vehicle can create a blind spot. So even advanced sensor or advanced AI could not able to proceed further and sense beyond the blind spot. So, what as our research community, both from computer science and communication background, we argue that we also focus on AI and as well as advancement in the automated vehicles and sensor. But we also argue that the vehicles needs to be connect with other vehicles and also with infrastructure, which enables a lot of information given to the vehicle so that it can make an informed decision within a given latency. The latency we are talking about is in microseconds difference in order to enhance the safety and efficiency. So this technology broadly we refer it as vehicle to everything, where vehicle connects with the infrastructure and with other vehicles. So how can we do research in this transportation system? Because it includes AI, it includes sensors, it includes communication. So how we can do the research? So for that, as people who have studied networks or communications would have already known about this, the protocol layers, where you can see from this figure. But for intelligent transportation system, the standard bodies such as IEEE and European Telecommunication have been developing these standards. So people who are not from computer science background, we just think about it's a sandwich. Okay, think about different layers of sandwich, and each layer we talk about rules and algorithms in order to make the packet from transmitter to receiver successfully possible. So there are different layers that has been classified, and we could we are actually doing research in almost all protocol stack in all slices, for example. So in access layer, which is the very low layer, which focus on the radio communication between sender and receiver, and as you know, there are two different main technology which is based on Wi-Fi and cellular, and we are working both on this, particularly focusing on intelligent transportation system. And as you can see from this below figure, that is just to efficiently manage the time and the frequency domain that the radio network is working on, and it's a very low level. And in a bit higher level, which we refer it as facilities layer, where we define there are different types of information that can be exchanged with respect to this automated vehicle. For example, as you can see from the first figure, vehicles can share its own information, and in the second figure, vehicle can share the sensor information, and in the third figure, you can see that vehicle can share also its driving intentions. So as informations are different, and the size and the rate can be very different. So think about a LiDAR sensor information that needs to be shared between vehicles. So it's a gigabytes of data that we are talking about, which could easily congest the network. So here we need to have this research question, how we can efficiently transmit this information, but still we sufficiently achieve the safety and the efficiency that we expect. So in this case, all the domains that was previously discussed, the AI, quantum computing and other factors comes in order to optimize when, what, and how the information can be exchanged efficiently. This is in facilities layer. And then we have this application layer. So once you receive different kinds of information, and what you're going to do next with that information. So you're going to process it and try to control the vehicle, right, in order to improve the safety. So that can be different cooperative applications. As you can see from the first figure, that can be using that information, you can enable cooperative driving or the other cooperative applications such as lane monitoring or collision avoidance and so on. So what I mean is, as you can see from this left figure, so research can be done in different ways and in different layers. So AI is just a tool that you can apply in order to optimize, but even with mathematical models and algorithms, you can do the same research. But what I want to say is, at the end of the day, we want to improve the safety and efficiency by actually in the lower layers controlling the radio network, or at the top layer you just controlling the message, the information itself. So so we do research based on the hardware based research, where we have this hardware devices in order to test and do the research on the top layer. And we do for below layers, we need to test with 1,000 number of vehicles. So real time analysis is not very difficult. So we do it through analytical modeling. So for that we use different simulators. And so why you need to join IIT Delhi? So for prospective students, so as many of the professors have addressed this before, so we don't just train students to for you to get a good job. We also train students and help you to create new jobs, and innovations, and to be an entrepreneur. And I believe these kind of AI and applications such as healthcare or this intelligent transportation system, which is a very new domain, which enable you to be an entrepreneur and create jobs rather than going for a job in an already existing company. So if you are interested in working in this AI or 6G in connected vehicles or in quantum domain, please connect with the professors here, or you can write to me. And the QR code, you can take a photo of it. Please go through the website of CART department as well as Bharati. In CART, we focus on this automated vehicles. People work in different verticals. And in Bharati, we mainly focus on communication part. And thank you very much. Yeah.
Thanks, Professor Gokulnath. So now we are open to the questions. Do we have any questions from the audience? Someone can please, do we have volunteers here? Can you please take the mic? So please mention the question is for whom exactly. The question is from there.
My question is for the sir who mentioned about the autonomous cars. Why do we need communication between the cars when we can directly say the car to drive? Why do we need the communication between them? Isn't it a security threat, something like that?
We mentioned this about, so all the automated vehicles will have its own sensor. Okay, so the first thing, the automated vehicles will rely on its own sensor, but as I mentioned, it has its own limitation, such as the range and say for example, if some other one vehicle is in front of it, it cannot detect further. Whatever the advancement you make, still the sensors has to be have limitations. But still the vehicle will drive through its own sensor, but the communication will act as complementary, which will give more information or the redundant information to the vehicle, which enables the automated vehicles to increase the confidence of the detected objects, so it can enable it can make the decisions correctly. And you can add more about the vision and the tracking and detection, so why apart from sensor, there are still limitations with AI predictions and so on, and communication could complement on that.
I'll give an example, like of occlusion. Do you know what is an occlusion? Anyone knows? No, right? Someone volunteered? Okay. So think of it like a Indian road scenario, okay? And you are driving a car, in front of you there is, let's say, another car, okay? Then in the front of you, you have like a truck, okay? The truck is there, but how much of truck do you think that your camera can see? Really not much, right? This is an occluded object. So similarly, then in front of the truck, there might be another person crossing the road and it will be like totally invisible, right? So the autonomous driving, especially in the Indian scenario, this is nowhere near a solved problem. The problem is much more like, if you think about in the European scenario, the American scenario, you can think of it as much more solved. I will not say that it's solved even there. But in the Indian scenario, even to make a proper identification between the road and the pedestrian path, we humans cannot make this separation. So how do you think that our AI system will make the separation? The vision research in terms of the automated car, I will not say autonomous, right? Automated is the right word, right? Vision research in the direction of the automated car, this has huge gaps yet that needs to be filled in the coming years.
So if the cyclist is connected to the car, so even if the vehicle cannot detect the cyclist using its own sensor, using communication, so it's complementary, but still vehicle will act with its own sensor and the communication will act on top of it, which complements with more information. I think we hope we address your question.
Question? There is one question from yeah, we.
Okay, I will. Yeah, I understood. So, yeah, understood. So I will just answer this with a small story. Okay, so initially in India or in the world, so the transportation system was used basically horse cart and bullock cart, right? And then we slowly started to use lorries and buses. So when there is a transformation happening in the beginning, or most of the vehicles are getting punctured because of the roads are basically the mud roads, not the typical road that we have right now. And there are the bullock cart shoe, no, the metal was lying around and it's got punctured. So so how do they solve it? So they have all the components of the bus and gears, motors, and so on, but still they cannot able to solve it. And they have think about innovation idea since they are in the boomer generation. So they put a magnet in front of the bumper and start to ride so that it picks up the metals in front of, so that the puncture or getting punctured, the vehicle is getting punctured or reduced. So what I mean from this story is just every technology in the beginning has been frowned upon, but later it will be implemented, and then during the transition it will be adapted and implemented. So so in order to, I agree that in India it will be very difficult, but so that's why we are I'm working with different government, both central and state government, and we are developing standards for incorporating this intelligent transportation system, developing standards as I mentioned in the different layers in the protocol stack. So what we are basically doing is, we are not, the automotive industry partners are focusing on developing the vehicle. As a government, what we are focusing on is not developing the vehicle, but developing the infrastructure. So in order to accommodate the vehicle in the road, we need to facilitate the infrastructure. So where we had initially mud roads to the now the roads that we have. So in order to accommodate the automated vehicle, we need to also focus on developing the infrastructure, which will takes time, but of course it will be implemented. So as of now, when we think about adapting these automated vehicles, we think it's not going to happen in India, but slowly it will happen. Right now, some of the projects has been already approved, not directly adopting this automated vehicle in the normal road, but there is a concept called autopods, where there is guided lanes and the automated pods, it's like a mini vehicle where 2 to 6 passengers can sit. So it is being tested for last mile connectivity, like from airports between terminal to terminal connectivity, or some pilot projects has been approved by Patna, I believe, recently, and we are also in talk with other state governments such as Telangana and Uttar Pradesh. But of course, yeah. So to answer your question, it is possible, but it takes time. So slowly, we also focus on this automated vehicle, but also we have to understand that we also need to develop the infrastructure in order to accommodate this kind of technology. Thank you.
So may I add a small point to this? So I am not an expert in intelligent transport system, but I see that we are always using this Google Maps, which tells us the congestion, right? So what it is doing, it is basically somehow collecting the data from other transport vehicles, right? And telling us that, okay, which path we should choose to avoid the congestion. So it is in some form, we are communicating among the vehicles, right? And we can also integrate it like in some other form, but still it is in some sense communication among the vehicles. Right? So.
I have a point to add here to Gokulnath's answer. The same technology that is used in deepfake example I gave before, the generative AI, that will, my personal belief is that will also play a very important role in the eventual adoption of the automotive vehicles in India. Because with the generative technology, what's possible is that to synthesize different scenarios, which otherwise we would not be able to imagine. And the the issue is that in the Indian driving scenario, this presents so many unique challenges, right? However, this all can be, like foreseen, okay? Foreseen by use of the generative AI. So I believe that generative AI, adoption of the generative AI will also play like a very important role to eventual adoption in such a complex traffic scenario of the automotive vehicles. Yeah. We had a question from there.
Thank you, sir, for this giving me this opportunity. This is more of a general question. So we are a country of 1.4 billion people. If we believe the data of American states, we are the most we have a most population in the world. So we are empowering the AI, but the brain training in India, educating the brain is lacking behind in terms if I compare to the AI. So what will be the negative consequences? And we are also machinizing our brain. We are making neural link, as I mentioned. So though human brain is more complex because of our evolution, but machines are growing faster and faster, and we are empowering AI. So I want to ask the negative consequence. And second thing, if we machinize our brains through the AI, then machines
machinize our brain to the AI.
Machinize our brains like Neuralink and empowering AI. So what will be the negative consequences? Because machines are more prone to be hijacked. Though brain can be manipulated, but machines are more prone to be hijacked. So what will be the negative consequences? More focusing on empowering AI, then I'm thinking we should also focus more on the brain training, because India is a country of vast population.
Okay. So this is more in the direction of the responsible AIs. I will request Professor Bhaskar to initiate the answer. Maybe we'll also join.
Because I understand it better, that if we are a population of 1.4 billion, why don't we focus more on our human resources, like training our population to be more efficient, and making AI systems better? Is that the correct interpretation of the first question? Okay. Let me answer the first. We only go to the second. So now you see, we have training our population, but in the other front, the technological advancement has to happen, right? So both has to go in parallel. You cannot do either one or other, right? We have to do both, first of all. So that is a basic straight answer. And now we can also imagine that whether AI can help us to make the education better, right? There is certain possibility in that aspect, that front also. For example, you can think of personalized tutoring. For example, each of us in this hall have a different level of understanding about certain subjects, right? Not everyone is at a same stage. But if a professor teaches to the entire audience, right, then they cannot address the individual understanding, individual needs, right? So we prefer for better teaching a small class like 10 or 20 so that we can make individual collections. But since we have a 1.4 billion populations and we want to improve the quality of education, it's very difficult to make it personalized. So there is a possibility that AI can help in that aspect. So we need to do both, right? That is my understanding.
I will add also another point to this. So this is, in my personal opinion, this is a bit unfortunate that, okay, we are right now sitting in a country which has 1.4 billion population. It was not so when we were a kid, like we literally saw going into that 1 billion, right? However, I'm saying that this is unfortunate. However, I also always find people who tries to defend this population growth. They say that the common logic that is used is that if there is not a population growth curve doesn't keep on going, then what happens is that we end up having a more older people, and then who takes care of those older people, right? So to debunk this logic also, I will use the same AI or what Bhaskar was saying. I will say that, okay, with the development of the technology, with the development of AI, the older people will be taken care by the AI itself, the technology itself. You will not need any more such a steep growth of population to take care of the older population and keep on, repeatedly in each generation, keep on increasing the population itself. So at some point, we will probably be able to reduce the population, or at least saturate the growth of the population by use of technology or by the use of AI. Okay, so with this, I think we'll put an end to this session because we are getting late with the exhibitions, the department-wise exhibitions, which is happening outside. So before concluding, the last message that I would like to give is that the research around the data communication and AI, this is nowhere at near saturation. Okay, I hope the population comes near saturation, but this research is nowhere near saturation. A lot of research needs to be done in the next few years or next decade. And in IIT Delhi, this research is happening across many departments: computer science, School of AI, electrical engineering, CART, CARE, and even the policy research around these topics in the School of Public Policy. In addition, a lot of other centers are also involved with these activities, like Computer Services Center, the high performance computing, the 450 GPUs cluster that I mentioned about, that is taken care by them. So come and join us. There is not just a single department or single center which is catering to this research. Depending on your own skill, there might be different department or center which is more aligned to you. So on the behalf of the IIT Delhi community, I invite all of you to think about IIT Delhi as the next step for your education. Thank you all.
So we have a couple of interesting demonstrations outside, and it's not going to bore you with more additional information. A couple of games are there, couple of demos are there. There's a robot which is going around. So after hearing 3 different sessions, one important driving message is that we work across academic units on key topics of national and international relevance. And you are most welcome to visit us whenever you want. But for now, please some fun time outside and have evening walk if you want to across the campus. Thank you again for coming today.